talking about, at the end of the last lectures, we were talking about nucleophilic substitution, and just realizing that if you do a nucleophilic addition reaction with our aldehydes and ketones, we know that they're reversible. Okay, so we know that when the nucleophile attacks the carbonyl carbon, we then break the carbon-oxygen double bond, we end up with our tetrahedral species. Now, we can just take an electrophile and protonate the oxygen to give us an addition product, but we also recognise that if the nucleophile was a leaving group, then we can reform the carbon-oxygen double bond and do the reversible process. So that leads us to say, well, what if there are other leaving groups available? Well, if there's another one available, we can get what's called a nucleophilic substitution. The nucleophile will attack the carbonyl carbon. We will then break the carbon-oxygen double bond. We form again our tetrahedral species in the middle here. And now because we have L, because we have this other leaving group, we can reform the carbonyl carbon and we can make that leaving group leave. And therefore we have ended up with a nucleophile substituting where the leaving group was. But what we need to remember is this isn't a nucleophilic substitution reaction. It is really an addition followed by an elimination. So if we keep that in mind, what we're now going to do is start looking at the reactivity of these more complex carbonyls, so where you've got not just a carbon and a hydrogen, not just a ketone and an aldehyde, but you've got other things, so for example a leaving group, and what happens if we add all of the nucleophiles we've looked at before. So we're going to start with looking at oxygen as a nucleophile. So if we react an alcohol with a carboxylic acid group under acidic conditions, we're going to get an ester product. So here we have our carboxylic acid, here we have our alcohol, we've got acid in our reaction mechanism, and ultimately we end up with an ester. Now, in this particular case where we get an ester and we get water. So this reaction is in equilibrium, and actually if we have this, it actually favours the carboxylic acid rather than the ester. So one way we can make it favour the ester product is if we can remove the water, so we can take the water out of the reaction mixture, then the reverse reaction isn't possible anymore because we've taken the nucleophile that would attack the ester away. The water would do an hydrolysis reaction, which we're going to look at in a few slides' time. Okay, so let's have a little look at the mechanism of ester formation. First of all, just change the colour of the pen. Okay, so if we have our carboxylic acid, okay, so we've got our OH group here. Well, we know that there's acidic conditions in here, so we have our H+, and we're going to do the standard reaction of the lone pair of electrons off the oxygen onto that proton. And what that ultimately does is gives us our activated carbonyl compound. We can then take our alcohol, in this case we're going to use ethanol as an example, but it can be any alcohol, and we're going to use the lone pair of electrons from the oxygen to do our nucleophilic attack. The carbon will have too many bonds at this point, so we then need to break the carbon-oxygen double bond. Okay, what that will give us is our tetrahedral intermediate. Okay, and this is the point where things get a little bit more complicated. Okay, so we've got acid in our system, and what can happen at this point is we can do what's known as a proton transfer. We don't know how it happens, or we can't say how it happens. We do know, but it can happen from so many different ways. In terms of, we've got acid in the system, the hydroxyl groups, for example, could pick up a proton. We might have some water in the system that we can use to protonate as well. But what it means is that what we can say is, if we think we can use this designation to say this is a proton transfer, we can write proton transfer. But what we're doing is saying, well, at some point, it's all in equilibrium, we can deprotonate the ethyl group. Okay, so we've removed this proton from here, but we can add that proton somewhere else. So for example, we can make this into H2 and it becomes H2 plus. Another way of just thinking about that is if we say, well, that OH has one hydrogen already, we can add a second hydrogen to it and we can form OH2 plus, which when it leaves makes water, and that makes a very, very stable leaving group, or very good leaving group. And then at this point we can use the electrons from this OH to reform our carbonyl bond. We have OH2 plus as our leaving group, and therefore we end up with a carbonyl with an O-ethyl group with a positively charged, and then we have water in the reaction mixture as well. And you need to remember, this is all in equilibrium. So it could be that the proton stayed on the O-ethyl group and we reformed the carbonyl and made that our leaving group, but that would just send us back to where we started from. To move the reaction forwards, we needed to protonate that oxygen and make the water leaving group. And then at this point, the final step is just to say we deprotonate and we end up with our ester. Okay, so here's a chance for you to try this yourself. So here is a different carboxylic acid. We're using methanol this time as our alcohol rather than ethanol, and we've got some acid in the system. Talking about at the end of